Hello students, welcome to today's session. Today we shall be discussing one important question based on the topic of percentage racemisation and percentage enantiomeric excess used in the topic of SN1. So the question has been sent by somebody from Maharashtra, so I am placing a video solution for all of you. So this is the dose for today and let us start with the session. So here comes the questions. Pause the video, start doing it and thereafter see into the discussion. So I hope you people have tried this question by pausing the video. Now what is being asked in this particular question, you are being given a alkyl halide. This is an alkyl halide given to you and this alkyl halide is being treated with water. Now this is a case of solvolysis. First you need to understand what exactly do we mean by solvolysis. Solvolysis is a process or is a reaction in which solvent itself start acting as a nucleophile. So this in a way always adopt SN1 type of a mechanism. As we proceed, I let you know what exactly are other details related to it. So now here in the question, this is being given. Now what is being said about the question, that this is X and this X has been replaced by OH because OH negative has water's OH has displaced this X negative and along with it H positive, HX has gone out. Now as a matter of fact, here what you are being given here is that this here in whenever in the organic chemistry during the reaction, if stereochemistry engaged, the question becomes very interesting. So what you are able to see is that after the reaction you end up getting two products and these two products are non-superimposable mirror images of each other, and so these are said as to be enantiomers. These two are enantiomeric pairs, enantiomeric pair. And this enantiomeric pair also you are able to get that this is which geometry. This is the retained geometry because the OH get attached to the place where the X was there, and now this is the inverted geometry. Why is it inverted? Because the configuration has inverted, and as we proceed I let you know what exactly is to be done in this particular question. So now the point is that in this, what are the options available to us? The options available to us are that if X is Cl, he is saying if X is Cl, the percentage racemization is more than had it been Br. If instead of Cl there is Br, he is saying in the case of Cl the percentage racemization is more. And similarly in the next option he is saying the percentage enantiomeric excess is more in case of Cl had it been not had it been Br, vis-a-vis if it compared with the Br in the case of Cl the enantiomeric excesses. So first we need to understand what exactly is racemization and enantiomeric excess, and in the last option he is talking about something in regard to ion pairing. So this video would let you know many aspects of the things that within one question you are able to see lot many other aspects of this. So first let me first define what is leaving group tendency, because what is there in this, that what difference is there if you talk of this particular reaction, only difference is in the chlorine and bromine. So and chlorine or bromine or chloride and bromide when goes out would be treated as leaving group. So leaving group tendency means that if it is a nucleophilic substitution reaction where this is delta negative, this is delta positive, and this is the incoming nucleophile which is attacking this carbon which is carrying a positive charge and throwing this X negative out. So in nutshell, I may say it like this: this is our substrate, this is our substrate, this is incoming nucleophile, and along with it, what you are able to get is the product, and this is what you call it as leaving group. Now, as regard to the leaving group tendency, that the one which is going out, if this is going out, this would be treated as to be better leaving group if the leaving group is stable, if it is stable. And if it is stable, that means it would not interfere with the product and to give back the reactant back. So we need to understand that somewhere down the line, if we are able to stabilize the leaving group, then the corresponding nucleophilic substitution reaction would be fast. One way of saying it this way. So now leaving group tendency is to be dealt in this case of halogen halides, because this is the case where chloride is to be compared with bromide, or am I shall I write it like this: fluoride, chloride, bromide, iodide. This is the one which we are supposed to compare. So if I talk of acid, HX is an acid and X negative would be its conjugate base. So if the conjugate base is stable, if I say that if conjugate base is stable, if it is stable, corresponding acid is strong. Corresponding acid is strong. Is strong. Now, if corresponding acid is strong, or reverse way, if the acid is strong, the conjugate base is stable. Stabler the conjugate base, stabler the conjugate base, weaker the base is. Weaker is the base. Am I right? What does it mean? If this thing becomes stable, it has lesser tendency to go the reverse way. It would not want to accept H positive. So stable the conjugate base, weaker is the base. And stabler the conjugate base, weaker is the base, better is the leaving group. Better is the leaving group. Here I would directly or categorically do let you know that sometimes people start comparing leaving group tendency with nucleophilicity. Make it a point, nucleophilicity do change with change in solvent. So it is always advisable when you are when you are talking of leaving group tendency, either compare it with basicity of the conjugate base or with the acidity of the acid of the conjugate base. So either through the acidity, stronger the acid, stabler the conjugate base, stabler the conjugate base, weaker the base, and better the leaving group it is. So considering the fact here that if I talk of the acidity of HCl versus HBr, because we are supposed to discuss first the chloride and bromide only. Let me place it here first, chloride and bromide only. So if I talk of acidity, HCl is a stronger acid, or rather reverse way, HBr is a stronger acid. Why? Because the stability of conjugate base, if I talk of stability of conjugate base, Br negative would be more stable as compared to the Cl negative. Because of the bigger size of bromide, the negative charge would got disposed better, so Br negative would be more stable. So here you should remember that the leaving group tendency in case of halide ions is fluoride is not the good leaving group, whereas chloride is better than fluoride, and iodide is the best leaving group. So what I suggested, that when you are interested to know the nucleophilicity, or you want to compare nucleophilicity with the leaving group tendency, I would not recommend. You always have to ensure the fact that leaving group tendency is to be compared either with the acidity of the corresponding acid of that conjugate base or with the stability of its conjugate base. That would give you foolproof answer, because nucleophilicity do change with the change in the solvent and some other factors also. Now, as regard to this particular problem, the two products which we got, as I said, these are nothing but an enantiomeric pair, and both of these are optically active. So this is having this is having chirality into it, and this is optically active. And since it is optically active, it would have one of its enantiomeric pair along with it. So both of these are said as enantiomeric pair. Now, what exactly is an enantiomeric pair? An enantiomeric pair is the one which are non-superimposable mirror images of each other. This also is optically active. This also is optically active. Now you have to remember this thing, that if pure of this compound is rotating the light by 40 degree, this would be rotating it with minus 40, or vice versa. The magnitude of rotation of magnitude of rotation of light in the case of one, if it is 40, in the two it would be minus 40, or vice versa. So the magnitude would be same, only the effect of rotation would be different. Now the point is, if these two are formed in equal quantity, then we say it has to be racemic mixture. So what exactly do I mean by racemic mixture? Racemic mixture, if these two quantities are formed in equal amount, then we will say it has to be racemic mixture. Now what is it, racemic mixture? Racemic mixture is a equimolar mixture of two or more equimolar mixture of two enantiomers. Now it is optically inactive, because if it is rotating plus 40 and this is rotating minus 40, and in the solution mixture it is equally present. This is 50% available. This also is, the molecules are 50. Out of the 100 molecules of this particular compound, 50 are in this form, 50 are in this form. That is what you call it as equimolar. So the point is that when they are 50-50 present and rotating the light, one by 40, another by minus 40, obviously the optical rotation would be 0, and then it would become optically inactive. So here it is to be remembered, it is optically inactive due to external compensation when the two enantiomers are in equal quantity. When they are in 50-50%, 50% is to 50%, then I would say, then we shall say percentage racemization, percentage racemization is 100%. Percentage racemization means that how effectively they are cancelling each other's optical rotation. If it is 50 molecules of this rotating by 40, 50 of this rotating by minus 40, net resultant of the light which came out of the um, spectrometer would be having optical rotation 0. So then it would be optically inactive. But if this quantity is not 50-50%, when it is unequal, we shall be saying that there is racemization, but it is not complete. And then one would be in excess quantity, would be said as enantiomeric excess. This is what we have written here. When the percentage of two enantiomeric forms is unequal, then the one which is in excess is called as enantiomeric excess, and the one which is the one which is in the one which is in excess obviously would show some optical rotation. That is what you call it as enantiomeric excess. So let me complete once again for you what I just have concluded, that if I say 1 and 2, these are the enantiomeric pairs, and if the percentage of this is 40 and that of this is 60, then I shall be saying that 40 molecules of this and 40 molecules of this got racemized, and 20% is percentage of enantiomeric excess. This you have to understand. Here what I said, that this in case, if these 1 and 2 are an enantiomeric pair and the percentage of this is 40 in the product mixture and this is 60, then I will be saying that the percentage racemization would be 80%. Because when, now what has happened, if it had been 50-50% racemization, if it is 50% available, then the percentage racemization is 100. But when it is 40% racemized, because 40 of this would racemized with 40 of this would cancel the 40 of the 60%. So that means 40% is going to get racemized. So when the percentage is 50, then the racemization is 100. When it is 40, then it would be 100 by 50 into 40. That is what you call it as 80%. This is the best way to identify the percentage racemization and percentage enantiomeric excess. Now the question is, now what has been asked in this question? So I gave you the insight, what are the things given to you. Now what we have to compare here. So he's saying that if in case we have taken CL in here, if we have taken CL here, then the percentage racemization is more than that of DR. So for that we need to understand now the mechanistic viewpoint. So the mechanistic viewpoint of SN1 is that first of all, this halide ion goes out because of the presence of polar solvent. This undergoes ionization, X negative goes out, and resulting in the formation of carbocation, because this dot electron which was of the carbon is taken out by the Cl or X negative. Now since carbocation is planar, because this is tetrahedral, now what would be the fate of the stereochemistry? So it would look like something like this. So it is CH3, here you would get H, and here you have gone pH, and what gone out is X negative. So what you have generated is a carbocation. So what I have did is, I hope you might be aware of the fact that this is the tetrahedral. Now once this gone out, now around carbon there are 3 bonds available, and 3 bonds would like to occupy a trigonal planar shape. So it is going to acquire a trigonal planar shape, and with the formation of positive charge on the carbon because X negative has gone out. So that is what I have shown it with the this vertical wheel, or or for the better understanding I will place here as to this got a positive charge. Now once this positive charge has been created, now what would be the next fate of affair? So the next fate of affair would be, this is what you have written H, and this is the pH, and you have got a positive charge here. Now incoming nucleophile, that is the water, now would can attack from this side or it can attack from the back side. There are two possibilities available, and in the process what would be formed, is something like this. Again, this would become this, and here you would get OH and here you get pH, or here another way is OH, or this would get HCH3 and pH. So there are two possibilities available. There is two types of attack possible. One attack is from the front side. It is the front attack. If it is the front attack, you would get the same thing which we have started with. So you would get the retained geometry, because this, why we are saying it as retained, because on this side earlier the Cl was attached, and if you are attacking it from the backside to the backside of this, so what shall you now be getting is the inverted one. Now the point is, we have to figure it out that what would be the fate of the thing, because of the fact that when you replace this X with Br or Cl, what shall be the product formation, that how this retained and inverted products get a bit changed. Now the point is that here we got a very interesting logic here. Now once this carbocation has been formed, let me show it like this. Now in the case of Cl, now first the Cl gone out and you end up getting this thing, CH3H and pH, and if it is Br, this goes out and you end up getting CH3H and pH, and here you would get a positive charge, here you would also get a positive charge. Now the point is, since Cl negative is not a good leaving group compared to Br negative, because the leaving group tendency of Br negative is better, Br negative is better than that of Cl negative. Now what would happen, since Cl negative although has gone out, but it would try to remain on the side from which it has came out. So this is what you call it as intimate ion pairing. Intimate, or simply I may say this is a sort of ion pairing. Ion pairing in the sense that Cl would love to remain on the side from where it has been departed, because it is not a good living group and it want to remain on the side, or I may say this side of this thing, of this carbocation is blocked for what? It is blocked for the attack of the nucleophile, which we are going to do. Versus here the blocking would be more, because Cl would not like to go away from the positive charge compared to Br negative. Br being having a better leaving group tendency, it want to remain away from this carbocation. So here the blocking which we are getting, this blocking which we are getting for the incoming nucleophile would be lesser. What I am trying to explain it, let me explain it once more for you people so that you could understand it better. I am simply saying it this way, that obviously the attack of nucleophile in both the cases from the rear side would be better, because there is no blockage, because Br has gone from this side and Cl or a nucleophile is attacking from this side. So this is always better, no doubt about it. But this would be better if the mechanism would have been SN2, that when the bond breaking and making had happened simultaneously. But here the clear-cut carbocation has been formed. Now what we are saying is, since the carbocation is being formed, it can be attacked from both sides, front side and back side. But the front side from where the Cl negative has gone, Cl negative being a little less Cl negative being having a more intensified negative charge as compared to Br negative, it would like to remain on the side of the carbocation thereby just blocking the attack of nucleophile or nucleophilic attack in the case of Cl is bit blocked from the front side compared to that of Br negative because of a stronger ion pairing shown by carbocation and Cl negative, because Cl negative has more intense negative charge as compared to the Br negative. So here what we have understood, that in both cases inverted product definitely is going to predominate, but in case of Br negative, inverted product would be formed lesser, because here the blocking is less, here the blocking is less. In the case of Cl, here the blocking is more, blocking or hindrance is more, in the sense that Cl negative and nucleophile would repel, but here since Br negative is distant apart, so the nucleophile can easily attack. So what we shall be saying here is that in the case of Cl negative, in case of Cl, we shall be seeing that inverted product is formed more than Br negative. In other words, since inverted is formed more, let me write it like this, that in the case of Cl and Br negative, just to make the things in a simple notion so that you can understand it better, I may say it like this, that in the case of Cl negative, if I say that the inverted product versus retained, let me write it like this, if inverted product, in both the cases inverted product shall be more, but here we are not being given the data, so we are not going to quantify it. Just for your sake, for your understanding, I may say it like this, that the inverted product in the case of Cl, let's say it is say for example it is 60%, so and here in this case it is 55%. So what shall it be saying, that here it would be 40%, retained would be 45, and in retained would be 40 in the case of Cl and 45 in the case of Br. So what does it mean? That if inverted is more, if inverted is formed more, so percentage enantiomeric excess in this case, so or rather first I write the percentage racemization. So percentage racemization in this case, because 40 of this would racemize the 40 of this, so percentage racemization would be 80%. In this case, 45% of this, 45% of this got racemized, this here would be 90%. And percentage enantiomeric excess in this case would be 20%, because 20% is in excess, 40 got racemized, here it is 10%. So this is what is being asked in this question. So the question was quite challenging at I think I'm able to explain the things better. Now see what would be the answer available to us. So what is to be done in this question? Firstly, you need to understand the fellow has asked the correct statement. Now correct statement would be when X is Cl, the percentage racemization is more. Percentage racemization is more. This is compared to the Br. So this is a wrong statement, because in the case of Cl, percentage racemization is less. Percentage racemization is 80%, and here it is 90%. You can take it like this. And for the second point, if I share it with you, second is if Cl negative is there, percentage enantiomeric excess is more had it been Br. So this statement is right. And C option is all of course would be wrong. Percentage racemization is same. No, it would not be. Ion pairing in case of Cl, ion pairing is weaker in case of Cl. No, in case of Cl, ion pairing is stronger. So now let me conclude what we have done, that if in case you are having Cl would going to get do the ion pairing stronger. So the side from which the Cl negative has departed, it got blocked, because Cl would try to remain onto the side from where it has came out as Cl negative. So thereby hindering the path of nucleophile. As a consequence, nucleophile is going to attack from the backside more compared to the case of Br negative. So in the case of Cl, the racemization would be definitely lesser, and percentage enantiomeric excess would be more. Now, just to elaborate it in a more better way, another one more question can be done here. So what is the question asked in this particular statement? So in the following reaction, the optical rotation of pure A. So what is A? So first you have to understand again here the halogen is being given as Br, and this is SN1, that is nucleophilic substitution, and this is what you can say it has to be retained, and this is the inverted one. Now what is being given is that if in case the pure A is minus 30, if you had with you pure optically pure A, its rotation is minus 30. This is what is being given. And during this reaction, the percentage of A and its percentage in the product mixture is 45%. So he is saying that this is 45% and this is what, if it is 45%, obviously it would be 55%. So the same analogy which I have taken in the previous question, so it got applied here. So what you are supposed to ask, supposed to tell is the optical rotation of the product mixture, that this product mixture would have what type of rotation. Obviously if it is minus 30, because enantiomeric pair has a property that if a the enantiomeric, the mirror image of this would be rotating the light to a same extent but in opposite direction, so the optical rotation of this would be plus 30. And since it is plus 30 and its percentage is more, so the final answer definitely would be positive. So A option get ruled out. It cannot be negative. It would be positive. Now, if I have to ask you in the question, what is the percentage racemization? So the percentage racemization I may say here would be, because the 45% of A got racemized with 45% of B, so the percentage racemization would be 90%. How do I get it? If A had been 50% formed, then percentage racemization would have been 100%. But since it is being formed how much? Since A is formed 45%, so the percentage racemization would be 100 by 50 into 45. So it is what? 90%, which we have already done, although it is not being asked. And if I say enantiomeric excess, percentage enantiomeric excess, percentage of enantiomeric excess obviously would be 45 of this racemized with 45. So that means the 10% enantiomeric excess is there because of B, that is of the inverted. And obviously the one which is formed in excess, because 45 got racemized, this 10% is in excess. So the optical rotation of final product of course would be 10% of plus 30, 10% of plus 30, and 10% of plus 30 is plus 3 degree. So plus 3 degree is being given as the answer. The answer to this question should be C. Another way to do the same question, because I have done two more questions along with the problem solving, so that in case you get this sort of a question, you are able to do it. So another way to say the same thing is percentage, sorry, optical final optical rotation of product can also be said it like this, that 45% of the first 45%, how much of the rotation it is going to do? 45% minus 30, because this is minus 30. So that is the another way to do the same thing. 45 minus 30 plus 55%, which is going to do the plus 30 divided by 100. So this value also would give you the 3. This is the another way to do the same thing. I hope you have understood these two problems. These were the questions being asked by somebody from Maharashtra. So I'm able to do the justice to the problem. Keep sending such questions. I would try to make the video solution of your queries. Thanks a lot. Have a nice day. Stay safe and take good care of yourself. Bye bye.